All right, well, I welcome you back to getting to hear me talk for a second time in 2 days. Today I'll be talking about something near and dear to my heart, which is secondary ion mass spectrometry. So, okay, make sure everything works. Good. All right, so Rick was just talking about OJ and XPS, where we have a situation where we're looking at photons or electrons coming in and measuring electrons coming out. With SIMS, it's much simpler than that. We are only dealing with ions. So we have primary ions that come in and secondary ions that come out. So it's an analytical technique based on that. And we talk about high energy ions in this case, which is very different than the high energy ions we were dealing with at RBS, where those were in the MeV region. These are only in the 1 to about 25 kilovolts. Key advantages of SIMS is that we are measuring ions coming out and the mass of them, and so therefore we can actually look at things like isotope differences, which you can't do with other techniques. Also, we're sensitive all the way down to hydrogen, which is not possible with many other techniques. So you can do hydrogen and lithium and such, and we have a huge dynamic range that allows us to really look at things with very low concentrations, well below 1%. So just following up on that technique comparison. So here's OJ and XPS that Rick had talked about, where we're measuring things. Spatial resolutions can get much better with the OJ than you can with SIMS, where we're limited. Rule of thumb, 1 micron, you can do better. As a matter of fact, a lot of the new ones are doing down under 100 nanometers with that. Sampling depths, though, tend to be very good, very close to the surface where you're measuring it. And where SIMS really shines is here in the detection limits. We can do parts per million, parts per billion in some cases. So that's really nice. Technique was really developed initially by the microelectronics industry wanting something that could measure their dopant levels. And so that's what really drove it early on. A downside is, of course, it's very challenging to get quantitative results, and we'll talk about that more later. But we can get elemental data and also some molecular data if it's only at the surface. And we can do decent work with insulators, although it is tricky. Generally, what I like to say is if you're looking for 1% and above, OJ and XPS are good. Some of the other techniques with the SEM, usually start there, and then when you need to go to lower concentrations, come and work with the SIMS. This is a block diagram of the SIMS technique. So of course we start with a primary ion beam coming in. This can be cesium, oxygen, gallium, gold. Bismuth is very popular now, and some other more exotic things that come in and strike your sample surface. And then we sputter away material. We had a nice talk earlier today about the technique of sputtering, so you kind of understand the billiard ball collision idea. You sputter away, and some fraction of that will be ionized. If it's ionized, we can weigh it because we can put a big electric field right in front of the sample through the energy analyzer, and then take it through a mass spectrometer, which separates them based on mass, and then we hit a detector. So detectors tend to be electron multipliers or Faraday cups. You can also have things like resistive anode encoders that allow you to get like an image, so it's actually a microscope. Or channel plates would do the same thing. Different types of results we can get are mass spectrum, so looking at the masses and the intensity of each mass. We can pick a peak and perform a depth profile or perform an image, or we can combine it all into an image depth profile. In SIMS, we tend to talk about 2 regimes that you're working in: static SIMS or dynamic SIMS. Dynamic SIMS is the older of the two, and that's where you're actually just constantly churning away and removing material. So if someone's going to say, is your SIMS non-destructive? You ask them, how big of an area do you need to be non-destructive? Because we are going to make a crater, especially if you're doing dynamic work. And so we tend to define that as a significant flux. Downside when you're doing all this churning for the sputtering is you tend to mix everything together, and so when you're doing depth profiling, you're really limited to elemental work, although there are now situations where they're getting past that, and we'll discuss that a little bit later. But this is key. Very, very high sensitivity, parts per million type things. Static sims came about later and is really neat because the concept is if we only affect 1% of the surface, is it really destructive? 99% of it's still okay. And so that's how we define it. So we say, if silicon has 10 to the 15 atoms per square centimeter on the surface and we affect less than 10 to the 13th in the experiment, then we'll say it's effectively the same. You can come back to the same area and get the same result. And when that happens, that allows us to see some molecular things. And so we get 2D surface images. And so of the instrumentation we have one that does a very good job for doing dynamic work and one that does a very good job for dynamic or static work. The Kamika IMS5F that we have is very good for doing dynamic sims. So we send a continuous beam in. It'll either be cesium or oxygen to hit the sample surface, and then we pull out the secondary ions and we bend them through an electrostatic analyzer, an electromagnetic analyzer, and through a final slit before they hit one of our detectors. So therefore, you're only measuring one mass at a time. You can quickly switch between them, but only one mass at a time. So it's very useful to know what you want to look for before you put your sample in. Finally, when we get to the detectors, we have a couple options. We can bend it over here to the electron multiplier for like 0 to 10 to the 5th counts per second. If we're going 10 to the 6th or better, you use the Faraday cup, and you try to avoid 10 to the 5th to 10 to the 6th. We can also do some imaging. This, like I said, this can be used as a microscope, an ion microscope. Although, to be honest, the newer instrument next door, the TOF Sims, does that a whole lot easier. How is the TOF Sims different? So instead of, and here we'll use a gold gun for our analysis, but we still have a cesium and oxygen a second gun that we use for depth profiling. So the way it's different is we're going to measure how long it takes for the ions to get to the detector. So therefore, you can't have a continuous beam anymore. So we spend a lot of effort in the TOF Sims making a ion beam that comes and hits the surface in a pulse with a very, very short pulse length. So therefore, we generate all of our secondary ions here at the surface at time equals 0. We still accelerate them away in an electric field, and then so we've given them a certain amount of kinetic energy, which we all know is 1/2 mass times velocity squared. So if you put a detector far enough away, all the light ones will arrive first, the heavy ones will arrive later. So you get a complete spectra for each pulse that you send in. In order to not have such a big room and get other advantages, we actually bend it through some electrostatic plates before it hits the detector. So that's one of the advantages there. In this case, the detector is a channel plate, so it gives us both the position and the counts. Ion beam sputtering is a very complicated thing. So we have the ion beams, the primary ions coming down in, hitting the surface. You can see down here we have a lot of the red circles stand for atoms in the material. The blue ones, of course, are our sputter beam. You can see we've got sputter beam coming down in and mixing all around. Our sample is getting all mixed up as well. We have some dopants here. And then what do we get out? Well, we get out all kinds of things, positive and negative, neutral species, mostly neutral species. We have some beam getting resputtered back. And the crater tends to have amorphous material and lots of bond breaking. So there's lots of things that are going on. We can get photons out, we can get electrons out, lots of things. So this is where I usually show a nice molecular dynamic simulation of an ion impact done by Professor Garrison at Penn State. She was looking at sending in a single gallium ion and the damage that's done on the surface, and then comparing it to a molecular, a C60 molecule. Because, as I was saying, doing depth profiling, you tend to lose the molecular information. From her work here, they decided to start using larger and larger molecules to allow you to do molecular depth profiling. And so if I can get this to work right. So this will be a gallium atom coming in. You'll see it hit the surface. You'll see one atom that sputters away. And just look at the size of the damaged area that comes in. So the yellow atoms are gallium atom. Here's our surface. You can see the various surface layers. I'm going to zoom in and boom. Saw the one atom come flying off. And then this is the level of damage that you're doing. All the mixing is coming just from one gallium atom hitting. And then this is the top view of it. Now, for the C60, here it is with the buckyball. Same thing hitting the surface. But now, look at how much stuff comes out, and you're going to have molecules coming out in addition to atoms. And the damaged layer is much, much smaller than what we were seeing originally. See if I can get the right window to come back up. There we go. All right, so talk about how to do quantitative work with SIMS. It's very difficult. We have this nice big equation here, talking about the secondary ion current is related to the primary ion current. The sputter yield, how many atoms come out based on what you put in. This factor called the ionization probability, and then information on what is the actual concentration that you're trying to get out, and the system situation. The difficulty we have is in this alpha term because it varies orders of magnitude, like it can vary by the order of 4 orders of magnitude, and so it doesn't vary in nice ways. You know, there's lots of things that can change it. You can have matrix effects. You can have different surface coverages affected, background pressures, crystallographic orientation, angle of emission. So basically what it comes down to is SIMS, you cannot, by first principles, get a value for quantitative. But on the flip side, if we use a standard sample, we have all these advantages. We can measure very low concentrations. We can get good results. So instead of looking at all these things as being a negative, let's try to use them to our advantage. Let's use surface coverage of reactive elements to enhance our sensitivity so we get more counts, so we can measure lower concentrations. And so that's what we tend to do with SIMS. So if you're up here in this part of the periodic table, you're generally with electronegative elements. And so if we want to enhance our signal there, we'll use a cesium sputtering gun. And that basically you can think of as the cesium has this extra little electron sitting out on the end, right? And it wants to give it away. It's not exactly how it works, but it's a good way to remember it. And so it's very easy to make negative ions here. Over here we have a situation where we have electropositive things. And so we'll use an oxygen sputtering gun. And you can kind of think of it, you sputter away a metal plus oxygen, and then the oxygen breaks off, but it takes an extra electron. So now you have a positive ion. And so those are easier to measure with positive ions. You can actually see this graphically here, where you're seeing, you know, the one on the left here is looking at M minus, metal minus, and so sulfur, oxygen, very easy to measure, but calcium's not so good, zinc's not so good. Over here with positive ions, calcium's good, magnesium's good, but the sulfur's not very good. You'll notice zinc tends to be bad in both cases, so therefore we tend to have to think of another solution for that. And so that they actually found out things for like zinc and cadmium you can look at by using metal plus cesium positive ion. And so there are ways around it in those special cases, and those are important for a lot of gallium arsenide work because those are dopants in that. How do we be quantitative then? We tend to use ion implants to get us a what's known as a RSF, relative sensitivity factor. You can define it this way if you're talking about a level profile or if you're talking about a Gaussian profile. But basically it's just a way to ratio the counts that you're getting from the matrix and the element of interest, the dopant, to the actual dopant concentration. So this is an example of ion implanted phosphorus sample. I'm going to use it. This would be what I would use to determine an RSF, but then I can also use the RSF to make concentration values. I ran this twice. I ran this in the good condition, where you would be using the cesium beam to do the measurement, and I also ran it in the bad measurement condition where you'd use the oxygen beam. Nice thing about phosphorus, it's group 5, so therefore it's pretty close. You can do it both ways. And so we have silicon signal up here. The vertical axis is the counts per second, and the horizontal axis is our depth. Generally this is in time, then you can use a stylus profilometer or optical profilometer to figure out how deep your crater is after the fact to get your sputtering rate. And so we get two things of signal, but then when you do the calibration, apply the calibration, you can get, they follow on, and you can see we're down here in the 10 to the 18 atoms per cubic centimeter. You'll see by doing it in the bad configuration, you have noisier data, but you can still get good results. One more definition that I want to throw out here real quick, mass resolution. So with like Rick's spectrometers and with the Kamika SIMS, where you're bending things through an electromagnet, the thing that's constant across the various masses in my case is the for resolution is m over delta m. So that's the thing that's constant. So that's the way we defined mass resolution in the SIMS. And so you look at your peak, you see the full width half maximum, and so you take the mass divided by that full width half maximum, that gives you your mass resolution, and that stays as a constant in the magnetic sector SIMS. And so, for instance, you know, you're on the, whoops, wrong. Yeah, here's your full width half maximum. With the TOF SIMS, of course, you're not using a magnetic sector, so therefore you don't have that. So when you're defining your mass resolution on a TOF SIMS, you got to also tell what mass you're using. So that's just an important thing to know. I'll also point out that we do a lot of plots that are on a log scale, because as you can see, the sulfur and the O2 here, you would not be able to see the O2 very easily on a linear scale. All right, that's it for definitions. Show some examples. This was a depth profile done of a gallium arsenide sample that was alternately doped with silicon and with carbon, and was annealed in nitrogen. And what this shows us is we do have the ability to follow the dopant levels. This is the carbon dopant level, this is the silicon dopant level. And also we can follow the hydrogen. And so you can see as you're annealing it, you're actually losing hydrogen to the surface. And so that may have an effect on the properties of the device that's being done. The other thing I'd like to point out here is that we have a very large dynamic range. So 1, 2, 3, 4, 5, 6 orders of magnitude on this plot alone. And we can see hydrogen. This is an example doing some isotopic analysis. Basically, we combined Auger results, Auger depth profile with the SIMS depth profile, where the Auger were following the various elements, and in the SIMS we're specifically looking at the two isotopes of oxygen. And by knowing which one diffuses, you can tell whether it's the metal that's diffusing or the oxygen that's diffusing. In this case, I think we had Ni3 aluminum sample that was being oxidized, and we found out that, if I remember correctly, the nickel and the oxygen both diffuse, but the aluminum does not. Example of a sample where I was more involved, we're looking at some gas source MBE of ultra-highly boron-doped layers. Things that jump out at me on this, of course, is we have these nice flat tops. So in the process, they were changing the boron doping rate. So they'd turn it on a certain gas flux and then turn it off, and then turn on higher gas flux and turn it off. And so we have nice flat layers, so that means our doping is very good. Very good. Here we're starting to see a little bit of a tail. So after you turn it off, there's still some boron on the surface that needs to be worked in. And that tends to get worse as you get higher and higher. But we were able to get up to some very high boron doping concentrations, 3 times 10 to the 20th. SIMS is also very good at measuring, not greatest plot, I apologize, but measuring very thin layers. And so these are some delta-doped boron layers as well. And so it shows how good of a depth resolution you can get with it, which can be on the order of nanometers. More recent example of some stuff we were doing, work with some people over at MNTL. They wanted a non-lithographic way to pattern wafer-scale nanostructures, but etching of highly doped arrays caused lots of pores and such. So the idea was to make the arrays lightly doped the surface, make the arrays, and then dope them with the spin-on dopant afterwards. We've done some previous results that showed that this works, and they could make the tips down here look very nice. So then the question then became, can we do, they wanted to make contacts to here to the tops, and so we did some more, and this shows some SIMS results where the dashed line is where the tips ended, and so you can see we have enhanced doping up near the top of the array. This was some work that we did with lithium-ion batteries. So lithium-ion batteries consist of a graphite negative electrode and a lithium-containing positive electrode, usually with nickel, cobalt, or manganese, and then an electrolyte. A lot of cases it's lithium phosphorus LiPF6. One problem that we see is there's an impedance rise at the negative electrode, and so the SIMS results that we did early on showed that we see a large rise of manganese and cobalt that diffuses from the electrode across, thereby poisoning the other electrode. So we did some additional experiments where we put down an alumina coating on the positive electrode, and then found that this caused, it inhibited the transition of the metals going across. Eventually though, if you aged it enough, you would see the aluminum going and the manganese going, but it helped increase lifetime significantly. So all these results that I was showing there was done on our Kamika SIMS, and that's generally was done in the dynamic mode. Find the cursor. In dynamic SIMS, so we had material removal, elemental analysis, and depth profiling. We can also do static SIMS using the TOF SIMS, and this gives us ultra surface analysis, elemental and molecular, and then the analysis is complete before a significant fraction of the molecules are destroyed. So the TOF SIMS is highly capable in that regime. One of the other things that's nice about it is how high a mass you want to go is how long you wait in between each pulse. So in theory, you could go to very high masses. This is showing a gold-coated sample where we're seeing clusters coming off up to 50 gold molecules in size. Generally, you don't get that good. The signal tends to drop off about 1,000 AMU. But with the TOF SIMS, we still have very good mass resolution. You know, you can, even though two things are the same nominal mass, like the gallium hydroxide and the gallium NH3, our mass resolution is quite high, being able to show us these things. You can see the shoulder here on these, again, all at the same nominal mass. We also have good lateral resolution. These are showing some indium arsenide quantum dots on gallium arsenide, and so some indium line scans, and you can see, half micron, about the size of these quantum dots. You can have very good depth profiling resolution. This is a aluminum gallium arsenide multi-layer stack, and it shows approximately 1 period for every 2 nanometers in depth. This was interesting, going back to some experiments then, this is an interesting experiment done with Professor Seebauer's group, where they're looking at the fact that you have a bending of the Fermi level near surfaces. And so we're taking advantage of the low energy 2 kilovolt gallium or oxygen gun in the TOF SIMS to do depth profiling. The experiments explore the interaction of a charged point defects near the surface region on the bulk diffusion in a biased sample. So they bias their sample during oxidation processes or boron processes. And so they can actually look at how things are moving in the field at the surface. And so they were able to make an analytical model, and some of the results there showed that the drift opposite to diffusion causes a pileup of oxygen near the surface. But if the drift in the diffusion direction would deplete the near surface of mobile defects. And so the vacancies can also be an important thing in this process as well, and those vacancies can tend to be charged. One downside to doing depth profiling in the TOF SIMS is you have to use 2 guns, and so therefore alignment of the 2 guns become very important. Ideally, we think of doing sputtering, and we're thinking we're going to have a square bottom crater, right? So that when we do our measurement here, all of our measurement is at the same depth when we do our work, right? But the reality is in SIMS, you tend to have something that's a little more curved, but that's okay, because if we do our measurement here just in the middle, we'll be okay, because it's, again, at the same depths. And you can get a nice result like this. This is some neodymium in uranium oxide that they did. The problem was, of course, whenever you're dealing with uranium, right? It's hard to have a lot of stuff, right? So his samples were really, really tiny. So he was trying to do his alignment on one sample and then do his measurement on another sample. And so in that case, you could end up where you're actually doing your depth profile over here on the side, and so therefore you've now spread out all of your depth information. You've convoluted it. And so his profiles tended to look a lot worse. So they started later, and then they looked a lot different. Takeaway here is you have to have samples that are big enough to do a couple spots on each one. Generally, if you're 0.5 centimeter by 0.5 centimeter, I can work with that. Generally, I like 1 centimeter by 1 centimeter. This was a neat project we did with Josh Ritchie. So he has this molecule that breaks under light. And so the idea was, can we see it? So what he ended up doing was he brought me a molecule that was completely covered with fluorines, and I said, can see it very easily. He goes, of course, that's not a very useful one to me. So then he came back with this one, and he said, what if I put a bromine on it? And I said, I don't know, let's try. And so we did, and what it turns out is a little hard to see right at the beginning, but you can actually pick up where he patterned it and broke the molecules. You see no bromine, that's here, and in the areas where the molecules are still left, you do see the bromine. What's interesting is you can actually see the effect of the sulfur, which exists in both, but is more screened when the bromine's in existence. And then this also shows the type of lateral resolution we can get. So this is a 50 micron scale. Can also do biological samples. This was some work done by Eric Monroe looking at single cell imaging in the TOF SIMS. Mass spectrum gives you peaks, but then of course the difficulty is figuring out what the peaks mean. So he used the advantage of being able to do imaging to help him figure that out. So what he found was if he's looking at a peak like the vitamin E peak here, and he had a fragment, another mass had a fragment, but the image looked the same, he could determine that those were related. And so this mass and the choline mass were had the same image, so they were also related. And so what happens is you tend to sputter away things, but they tend to fragment. The molecules tend to fragment, so you actually get a certain pattern. One of the new TOF SIMs that are coming out, they just announced it last year. They actually put a second mass spectrometer, so you can actually send a mass spec in, break that apart, and look at its constituents for the peak, and that helps you identify things. So mass spec is something that goes on a lot in the chemistry community. Another sample that was done, this one by Kenzie and Maya, was looking at TOF SIMs of the images of songbird brain. So we have a large sample holder that can be used, and this is actually a tissue slice cut from the entire brain of the songbird. And so he did a very large imaging and then stitched them together. So this actually consists of 194 600 by 600 micron scans. What they were trying to do is they know that if you put a new bird, a new chick, in an environment where it doesn't get to hear an adult sing, it'll never learn to sing. And so what they wanted to see was what were the changes in the brain. And so they found out that there are certain fatty acids that if they're not in the right spot in the brain, the bird doesn't sing. And so they were able then to determine that for development, the fatty acids were necessary. Good time here to throw in a little advertisement for the biological conference that will be coming up this fall. So just to let you know that that'll be coming up. And so TOF SIMs is used for biological work as well. Another thing that we're used for is friction testing. So a group from Argonne comes down and does pin-on-disc testing. And so they look at the effects of different lubricants. And so this is a situation where they had diamond-like carbon coating on their ball, and they would wear it until it failed and take a look at what happened. And then from here you can see that there's oxygen that's forming at the edge of the wear track, whereas there's oxygen at the edge of the wear track, where there's carbon pretty much everywhere. You can actually do an overlay plot to see the two of them. And so when you get to the failure, it's probably due to oxygen coming in and affecting the diamond-like carbon coating. Can also, from the TOF SIMs, make 3D models of the surface. In the software, you can actually rotate these around and look at them in different ways. And again, you can see the wear track here, where the oxygen is outside the wear track. And you can make movies, same type of work. So this is a movie as you go into the sample. So you start at the surface, you have a lot of hydrogen, and as you go through, you start losing it. So just to finish up here with a summary of the TOF SIMs. So we're using ions in, about 1 to 20 kilovolts of kiloelectron volts of ions coming in, and we measure the masses coming out. Can be up to 10,000 AMU in specialized circumstances. Type of information we can get are surface mass spectra, 2D surface ion images. We can do elemental depth profiling and 3D image depth profiling. We can detect all the way down to hydrogen and up. And our sensitivity can be from parts per billion up to atomic percent. Sampling depth tends to be about an order of a micron to several millimeters. Sampling depth tends to be in the nanometer type range. So thanks to our sponsors, and I'm willing to take some questions.
Questions? Yes?
Do matrix have a role in the sensitivity of increasing the SIM?
Very much so. Okay.
If the matrix will have a role in the sensitivity of
The matrix has a huge role in the sensitivity of the SIMs. It can affect it by orders of magnitude. I actually had a situation where I was measuring a copper film on silicon and looking at the diffusion of the copper into the silicon. And so I'm following the copper in the copper film, and all of a sudden, when the silicon comes up, the copper comes up. So there wasn't more copper in the silicon than was in the pure material. It's just the situation of the matrix effect. makes it so much more easy to see the copper in the silicon than it does in the bulk.
So the sample preparation will be almost similar to the multi.
Yes, there's a lot of similarities between MALDI and SIMS.
Sample preparation.
Yes.
Okay, we have some questions from Oklahoma as well. Is it possible to apply SIMS technique to liquid samples? If so, does this involve any special sample preparation?
I would say the same things that Rick said with respect to liquid samples. We have to put the material in a vacuum system, so it makes it very difficult. Although we do have a slight difference. There are techniques out there, DESI being one of them, where you're doing atmospheric mass spectrometry. And so there you can actually have a little device which shoots ions there, or finds a way to ionize your liquid and then use a vacuum to pull those ions in and then do mass spectrometry on them. So those are newer techniques that exist.
Can an MR, multiple reaction monitoring can be embedded with this type of technique?
Multiple reactions.
Yeah, that comes with the ESI.
Can you repeat that question?
Yeah, so basically I think what you're asking is, can you do multiple reaction monitoring? And if that's kind of like mass spec, yes, that is, as a matter of fact, the companies just started producing that. There's two major manufacturers of time-of-flight SIMs, and they both came out with their competing mechanism for doing that this past year.
Do you also need ultra-high vacuum?
You also need ultra-high vacuum?
Ultra-high vacuum works wonders for doing this technique because it's so surface sensitive. I will tell everyone when they bring their sample to me that I will see things like sodium and potassium and fluorine and chlorine on their sample. And they said, but I didn't have any of that in my process. I'm like, did you carry it over to me in air? Yes. Then I will see these things. So it is very, very sensitive, and that's the purpose of ultra-high vacuum, to get you a consistent surface for doing your work.